Today we shall discuss various expectation values, but let me summarize shortly what we did so far. We made estimates of size. We are studying H atom, hydrogen atom. Energy and the strength of the electric and magnetic fields. This was estimate. Then we started doing regular quantum mechanical computation, and we found the wave function, radial wave function, and this included associated Laguerre polynomials, where alpha is 12 plus 1, this is n minus l minus 1, and 2r over n. And then we studied the integral representation of the Laguerre polynomials in the complex plane, integral representation, and we obtained the generating function, and we also obtained the Rodriguez formula. And then using the green generating functions, we obtained the recursion relations of L alpha n's. And then we studied the Sturm-Liouville property of the associated Laguerre polynomials and their orthogonality. And we also used the orthogonality relation and the recursion relations to obtain the normalization of R and L. So normalization using these relations and the orthogonality and the recursion relations. Recursion. We basically used the recursion relation coming from the UG. So we have obtained the H atom wave functions. Today, we shall study the expectation values of various power of R. S is the integer power, and in particular, we will take S equals 0. Again, we will compute this normalization constant there, which we computed here, but with a different method. Then we will take S equals minus 1, S equals minus 2, and S equals 1. So we will compute these expectation values. Namely, we shall compute for these values. So this is this lecture's agenda. I will erase now the blackboard. We will do it like this. First, I will describe the general technique of taking these, and then, so that will be the general approach. Then we will take one by one. S equals 0 to build up confidence in the method, to reobtain the normalization constant. Then we will do these in succession. Well, our eraser doesn't really erase so well, so I'm using a wet towel, and each time I use a wet towel, video will cut so that I can clean up and it dries a bit, and you don't waste your time watching that. Now, we will compute psi NLM R r to the s psi n lm. Since we are computing the expectation value, since angle, does not depend on angle, and since these are orthonormal spherical harmonics, we really have r and l, r to the s. I am now explaining the general method before specializing to certain powers. So this is from 0 to infinity dr r square, and we found r and l as the normalization constant times r to the l e to the minus r over n l to l plus 1 n minus l minus 1 to r over n, and n and l was 1 over n over 2, 2l plus 3, 2n, n plus l factorial divided by n minus l minus 1 factorial and r and l times r to the s and another r and l. This gives n and l square, 0 to infinity dr, r square coming from the spherical coordinate, then r, l, another one from here, r to the 2l plus 2 and plus s. Then the square of it, one coming from the first, second one from the second wave function, 2r over n, and l 12 plus 1 square. Clearly, one should switch to another variable. Let's say x equals 2r over n, and r is equal to n over 2x. Therefore, this is equal to n l square. Now, how many r's do we have? 12 plus 2 plus s, and there is another one. So it is n over 2, 12 plus 3 plus s times 0 to infinity dx e to the minus x ln alpha x let me write it like this, alpha x times the power here, x 2l plus 2 plus s. So let me call this integral the integral that we need. Let us define it as j n of s. So let me erase here. Let me write this thing upstairs. R, S, and L for the short notation for the expectation value. That's equal to NL square n over 2, 12 plus 2 plus 3 plus s times j n and s. So we have to compute this integral. We will compute this integral using the generating function, which generates the associated Laguerre polynomials. I'm erasing this part. Consider the integral defined like this. From 0 to infinity dx x to the 2l plus 2 plus s e to the minus x. And instead of the Laguerres, let's write their generating functions. G alpha of un x, G alpha Tnx, and G is equal to sum over n. For example, let me take this one, un l, this is alpha n. Therefore, this is sum over n and m, un tm jn m s, where this thing is 0 to infinity dx x to the 2l plus 2 plus s e to the minus x l alpha n x l alpha mx. The point is that because of the simple form of closed form of g's, we can take this integral exactly. For example, this one is 1 over 1 minus u alpha plus 1 e to the minus x u over 1 minus u. So because of that simpler form of the total closed expression, this integral is doable. And that integral then is equal to un tm jnm integrals, which are in general these. Now, however, we don't, for the expectation values, we don't need these the general form. We only need the equal powers of u and t, and the power should be n equals n minus l minus 1. So we will find the power of ut raised to the power n minus l minus 1. That will be our integral, and we will put that in. We can write this integral, therefore, like this. I equal powers of u and t plus I non-equal powers of u and t. And I equal is something like this. I equal n, and I equal n will be ut to the n, j, n, and s. So first let's take this integral and then look for the equal power terms in I and take the power n equals n minus l minus 1. That coefficient will be j, n, and s, and that will go to here. So let me just take the integral. Let me continue here. This will be equal to 0 to infinity dx x to the 12 plus 2 plus s e to the minus x 1 minus u and 1 minus t alpha plus 1 e to the minus x u over 1 minus u e to the minus x t over 1 minus t. So let us collect the powers of the coefficients of x in e to the minus x. So it is e to the minus x times 1 plus u 1 minus u plus t 1 minus t. And the square brackets will read 1 minus u minus t plus ut. Now this one plus u minus ut, this one plus t minus ut divided by 1 minus u 1 minus t equals. Now let's see which terms cancel. U terms cancel, t terms cancel. This ut cancels that. So it is 1 minus ut divided by 1 minus u 1 minus t. Let's call it a. Therefore, we have e to the minus xa for this thing, where a is this. Clearly, it is best to switch, to change the variable again. Y is equal to xa, therefore x is equal to y over a. I can erase this part. So this I will be equal to 1 minus u, 1 minus t, alpha plus 1, times 1 over a. The power will be 1 over a, 12 plus 2 plus s. There is another one for this. 2l plus 3 plus s times 0 to infinity dy y 12 plus 2 plus s. Let me add 1, subtract 1, e to the minus y. And this is a known integral. This is gamma of 2l plus s, 12 plus s plus 3. But because L is an integer, S is an integer, this is 12 plus S plus 2 factorial. A contains power of 1 minus u, 1 minus t, as this alpha plus 1 power is 2l plus 2. So I can write the result of the I integral. I am erasing this part. I equals 1 minus u, 1 minus t, so this will be in the numerator, 12 plus 3, so it is 1 plus s. This is 1 plus s divided by 1 minus ut, this one, 1 minus ut to the power 12 plus 2. And 1 minus ut, this 12 plus 3 plus s, plus 3 plus s, and times 12 plus s plus 2 factorial. I can erase the rest now. So this will be written as I equal powers plus I not non-equal powers. So this will be of the form sum over n ut to the power n JNNS. And so we will take the equal powers of U and T like this. And when n is n minus L minus 1, the coefficient multiplying U and T goes to here. And that will be our result. Let me just copy this result upstairs and keep it there. And then we will use different S and adapt the formula for that. So I'm writing the general formula for that to top, and I want to keep that there. I'm erasing this. Let me write n equals n minus L minus 1. I'm writing I equals 1 minus U, 1 minus T, 1 plus S divided by 1 minus UT, 1 minus UT, 12 plus 3 plus S, these are pluses, times 12 plus 2 plus S factorial, which is I equal plus I not equal, and we will pick here ut to the power n with n equals n minus L minus 1. So I'm erasing this board. We start the computations now. I'm erasing. I'm just putting up a line. The first one, although we obtain the normalization constant using the recursion relation, and we know what this normalization constant is, still it's good to apply the technique and see that we can derive it with this approach. So 1, the average of 1, we demand it of course to be 1, that is NL square. We will try to find this. By the way, this is, that means S equals 0. Okay. This is n over 2, 12 plus 3, J n 0. So all we have to do is to find J n. We write this general form, insert S equals 0, expand, look at the equal powers of ut, and then pick that power, which is n minus L minus 1. So I is equal to, S is 0, so we have 1 minus U, 1 minus T over 1 minus ut. S equals 0, so this is 12 plus 3 times 12 plus 2, S is 0, factorial. And this is I equal powers plus I not equal powers. When I say equal powers, I mean the powers of U and T. So terms contributing to, so this is already in U and T, and we expand it, it will be in powers, in equal powers of U and T. But this one is not, because this has U and this has T. So the terms that are contributing to I, contributing terms to IAQ of 1 minus U, 1 minus T, that's equal to 1 minus U minus T plus UT. So we, when it has a multiplying, when you expand it UT to the K, this will make it UK plus 1. This will make it TK plus 1. So we do not include them. And so the contributing part will be 1 plus UT. All right, 1 plus UT will multiply this. So let us expand. 1 minus UT, 12 plus 3. That's equal to sum over K Now comes the binomial coefficient. 2L plus 3, the power, plus the index, minus 1, K, UT, K. Or sum over K. So this makes it 2. So it is 2L plus 2 plus K factorial divided by K factorial times 12 plus 2 factorial. Notice that this 12 plus 2 factorial will cancel with that. Therefore, I equal powers terms will be 1 plus ut, this thing cancelled, 1 plus ut times sum over k, 12 plus 2 plus k factorial divided by k factorial times here ut to the power k, ut to the power k. Now there are two terms here, no ut term and ut to the first power. So to get to ut to the n, we need two terms from here. Let's see which one goes with which one. One goes with k equals n minus l minus 1. That's the one. And ut goes with k equals n minus l minus 2. In both cases, the power of ut, total power of ut, will be this. So I am looking, therefore, sum of two binomial coefficients. This keeps breaking. Two L plus 2 plus n minus L minus 1 factorial divided by n minus L minus 1 factorial plus 2L plus 2 plus n minus L minus 2 factorial divided by n minus L minus 2 factorial. Everybody is multiplied by ut to the n, which is n minus L minus 1. So let's see what these are. That's equal to, this is 2L. So this is n plus L plus 1. And this is n plus L. So this is equal to n plus L factorial divided by n minus L minus 2 factorial n plus L plus 1 factorial. N plus L factorial is here, so we have only this term, divided by n minus L minus 1. N plus L factorial is out, and this is out, so it is plus 1, which is equal to n plus L factorial divided by, when I equate the denominators, this will go out, so it is n minus L minus 1 factorial times n plus L plus 1 plus n minus L minus 1. So this part gives me a 2n. We are finished. This gives as j n 0 equals n plus l factorial divided by n minus l minus 1 factorial times 2n. So I am erasing these. So all we have to do is put that result into here where s equals 0. So 1, this should be 1, is equal to n l square n over 2, 2l plus 3 times 2n times n plus l factorial divided by n minus l minus 1 factorial. And this should be 1, because that's the average of 1 in the state NL. Therefore, N and L is equal to 1 over N over 2, 2L plus 3, 2N, N plus L factorial divided by N minus L minus 1 factorial square root. So, if you remember, this is exactly the same result we obtained using the recursion relation. The recursion relation we obtained by using delta UG, by differentiating G alpha UX. Remember that last time we obtained the normalization condition using orthogonality of the associated Laguerres, and that the recursion relation we obtained from here. Here it's brute force integral, and we obtained the same coefficient. So we are done with s equals 0. All right, I am erasing, and we will move on to s to the power minus 1. All right, we will now do s minus 1. That means we will compute the average of 1 over r. So 1 over r in the state principal quantum number, orbital quantum number. This is n square n over 2. S is minus 1, so this is 12 plus 2 j n minus 1, and n is again this n minus l minus 1. All right, we will extract n from this integral. Here we put s minus 1, 1 minus 1, so this term goes. This is 12 plus 2, so it is 1 over 1 minus ut, 12 plus 2 times 12 plus 1 factorial. You see, the expansion of it only involves equal powers of ut. So this is simply equal composed of the expansion is composed of equal powers of u and t. Let us do the expansion. Let's take factorial here. 12 plus 1 factorial sum over k. 2l plus 2 plus k minus 1 k ut to the power k. That's equal to 12 plus 1 factorial this is now 1, 12 plus 1. So this is 2l plus 1 plus k factorial divided by k factorial 12 plus 1 factorial times ut k. So this cancels that. So we need the power of ut n, which is n minus l minus 1. So ut n, which is n minus l minus 1, is just this 12 plus 1 plus n minus l minus 1 factorial divided by n minus l minus 1 factorial, and this is n plus l factorial. Therefore, j n n minus 1 is n plus l factorial divided by n minus l minus 1 factorial. We will put that thing in here. In addition, we shall use the, now we have computed, in fact we computed via recursion relations and via through this method the normalization coefficient. So let's write 1 over r and l is equal to square of it is 1 over n over 2, 2l plus 3, 2n, and n plus l factorial over n minus l factorial times n over 2, 12 plus 2, n over 2, 12 plus 2, times j n n minus 1, which is this, n plus l factorial over n minus l minus 1 factorial. So this cancels that. This cancels, there's a minus 1. That. One over r. Twelve plus 2, 12 plus 3. So there is only one power of n over 2. And only 2n is left. So 2's cancel. So the result is 1 over n square. So I can erase this part. Calculation is finished, but I want to talk a little bit about this result, 1 over r, 1 over n square. I'm erasing this. We don't need this anymore. The calculation is finished. We computed j and inserted here, and we have the 1 over r. So I would like to comment a bit more on this relation. First, notice that we are using dimensionless r, and the physical r is just Bohr radius times r. So r is the scaled. So if you multiply this relation by 1 over a0, 1 over r physical is 1 over n square a0. All right. Another thing is when we made our equations dimensionless, namely we measured r in terms of just this relation a0, and we measured energy so we measured energy in units of the ground state binding energy, En over EB So if we do this, when we did this in the time-independent Schrödinger equation, we obtained the equation like this. So this represents the kinetic energy, this represents the potential energy, this is just the energy, total energy. So the PE in the state NLM is simply minus 2 over n square. Because it's minus 2 times the average of 1 over r, and 1 over r average is just n square. And therefore, kinetic energy average is equal to minus 1 over n square, this thing, plus that, plus 2 over n square. So it is 1 over n square. So as a byproduct of this calculation, we obtained that the expectation value of the kinetic energy in the state hydrogen atom state NLM is 1 over n square. So it's rather simple. Total energy is minus 1 over n square. Potential energy is minus 2 over n square. And the kinetic energy is 1 over n square. Okay, we are done with S equals minus 1. Let me just copy down this result here so that we have a list. 1 over r is 1 over n square. I am erasing it, and then next we will do 1 over r square. So I am erasing. All right. Now we will consider the case S equals minus 2. So we are taking the average of 1 over r square. So 1 over r square, I'm just copying from here with S equals minus 2 and NL square, which we know, n over 2. This is minus 2, so this is 2L plus 1, J N minus 2. So we have to compute this one. So let me write the integral for this. S is minus 2, so we have 1 minus u, 1 minus t, minus 1, and 1 minus ut. This is minus 2, so it is 12 plus 1. This is minus 2, so we have 12 factorial. This is sum of equal powers of u and t and not non-equal powers. When we expand it, this term, the expansion involves only the equal powers, but this one does not. So we have to collect the terms that have equal powers. So let's say 1 minus u is equal to sum over k1, u k1, 1 over 1 minus t, this one, that's equal to k2, t to the k2. Therefore, terms contributing to equal powers is simply sum over k ut k. Namely, from this double sum, we only use this one. This is the one that contributes to that. How about that one? One minus ut 2L plus 1 is equal to sum over p 2L plus 1 plus p minus 1 p ut to the p. Now when we multiply with that, again we are considering only terms that contributes to equal powers. So I have, let me write to the front, 12 factorial. Then I have sum over k and p ut k plus p, k from here, p from there. And then binomial coefficient 12 plus p and this p. Now, of course, there are many terms. To be able to control this sum better, let us multiply this 1 by 1. And I will write 1 like this, sum over r, that from 0 to infinity, delta r k plus p. So it is 1 if r is equal to k and p is fixed. You make the sum, r is 1 if k fits equal to the sum of k and p, and 0 if not. Now we will change the order, and one of the sums will drop because let's drop k. K will be r minus p. So it's equal to 12 factorial sum over r ut to the r sum over p 12 plus p and p. P goes from 0 to r now because it cannot exceed r. All right. Fortunately, this is a sum of the binomial coefficients, and fortunately there is a simple formula for this sum. And the result of this sum is 2l plus r plus 1, r is the upper index, and r. Which is 2l plus, let me just leave it there. Is equal to 2l factorial sum over r ut to the r and 2l plus r plus 1 r. Now, this is of course an infinite sum, but what we are looking for is ut to the power n, because the coefficient of ut to the power n, capital N being n minus l minus 1, will be our desired coefficient. So let us look at it at r equals n minus l minus 1. So it is 2l plus n minus l minus 1 plus 1 divided by n minus l minus 1 factorial. So what is this? One's cancelled. This is n plus l. So n plus l divided by n plus l, and this is n minus n, l plus 1. So this is 12 plus 1 factorial. So we have 2l factorial divided by 12 plus 1 factorial. And then n plus l factorial divided by n minus L minus 1 factorial, which is just this, this is 12 plus 1 times 12 factorial, so 12 will cancel that. The result is that. This is simply j n minus 2 with n equals n minus L minus 1. And we will put that result into here. So I'm erasing this part. This was computation. So we are done with the computation. This is equal to, I'm here. First, the square of the normalization coefficient. N over 2, 2L plus 3 times 2n times n plus L factorial over n minus L minus 1 factorial times n over 2, 2L plus 1 times this n plus L factorial divided by n minus L minus 1 factorial divided by 2L plus 1. I'm erasing this part. N plus L factorial cancels this. N minus L minus 1 factorial cancels that. So the result is equal to 12 plus 1, 12 plus, only the square will remain, 1 over n square over 4, then 2n, then 12 plus 1, but let me write 12 plus 1 like this to cancel the L plus a half. So this is 4, cancels that. So it's equal to 1 over n cubed L plus a half. We are finished. Let me just write down the result cleanly. I am erasing this part of the computation. So R and L 1 over R square, which is 1 over R square is equal to 1 over n cubed L plus a half. And if you are looking, this is the dimensionless. If you are looking for 1 over R physical square and L, so we divide by A0 square. So it is 1 over n cubed A0 square L plus a half. So this is the result, and let me just copy it here. 1 over R square is equal to 1 over n cubed L plus a half. Okay. We are finished with s equals minus 2. Next, we shall compute with s equals 1. I am erasing the blackboard. As the last computation, we will compute the average of R. So S equals plus 1. So this is n and L square. N over 2. S is 1. So this is 2L plus 4 times j and n plus 1, and we will extract j and n from this integral. S is 1, so I is, I'm writing the factorial first, 12 plus 3 factorial. Then s is 1, so we have a square upstairs. 1 minus u square, 1 minus t square divided by 1 minus ut. S is 1, so this is 12 plus 4. We can, of course, expand it, but let us look at this. This is I equal powers and not equal powers. So, contributing terms to I equal powers. This is equal powers anyway, but let's pick the so it is 1 minus 2u plus u square times 1 minus 2t plus t square. That's equal to, I am looking for equal powers of equal powers. Well, 1, then minus minus plus 4ut, then plus u square t square. Other terms will contribute to not equal powers. So this one, 1 over 1 minus ut, 12 plus 4 equals sum over k, 12 plus 4 plus k minus 1 and k ut to the k. And this is 3. This is 12 plus 3 plus k factorial divided by k factorial 12 plus 3 factorial. This 12 plus 3 factorial will cancel that 12 plus 3 factorial. So I equal is I am cancelling these, considering simply 1 plus 4ut plus u square t square times k, 12 plus 3 plus k factorial divided by k factorial times ut to the power k. Now we are trying to get the coefficient of j and n. So I want ut to the power n, which is n minus l minus 1. And there are 3 terms here. So 3 k terms will contribute to this sum. So for the first one, 1 will go with k equals, this will carry the whole power. So this is n minus l minus 1. Then 4ut, this will be associated with 1 less power, k equals n minus l minus 2. And u square t square will be associated with k n minus l minus 3. So that me just 12 plus 3 factorial cancelled. So the first one will go with the coefficient 1. So I will have 2L plus 3 plus n minus L minus 1 factorial divided by n minus L minus 1 factorial plus 2L plus 3. First, let's work it out because the others are will be subtracting from here. This is what? N. This is N. Then I have an L. Then I have a 2. Then I will have N plus L plus 1 factorial this will be associated with that, so it is 4 n plus L plus 1 factorial divided by n minus L minus 2 factorial plus the coefficient is again 1 times n plus L factorial divided by n minus L minus 3 factorial. In the last one, kappa is n minus L minus 3, so it cancels, n plus 3. So this whole thing is multiplied by ut to the n. So this is the factor j and n1 we were looking for. So I will erase the rest and then we will work out this this coefficient. I am erasing. Now I am carrying over from there. We have ut to the power n minus L minus 1. And this is the sum we need to evaluate. And since these are bigger than n plus L and n L minus 3, I take this one out. Let us simplify the inside the parentheses. N plus L factorial divided by n minus L minus 3 factorial times n plus 2 plus L plus 1 over n minus L minus 1. Next, the other term, plus 4 times n plus L plus 1. This is n plus L plus 1 times n plus L factorial, and n plus L factorial is here, it's out. N plus L plus 1 over n minus L minus 2 plus 1. Now, we multiply this thing by n minus L minus 1, both upstairs and downstairs, and we multiply that with that denominator. So let me multiply n minus L minus 1, n minus L minus 1, and instead of 1, we write n minus L minus 1, n minus L minus 2, n minus L minus 1, n minus L minus 2. So denominators are the same, so we can take it out and combine it to here. So it becomes n minus L minus 1 factorial. So this is ut, in short, let me call this n, which is just that, n plus L factorial divided by n minus L minus 1 factorial times. So the whole, these. Now, if you look at here, there is some symmetry appearing in the denominator. For example, n plus L plus 1 is also here. But n minus L minus 1 is also here. So, well, one way would be just to brute force multiply everything out. But another way, could there be some symmetry? Let's write this thing as 2 plus 2, and 2 of these terms, let's combine with that. 2 of these terms, let's combine with that. Denominator is out. I'm only working with the numerator. So it is n plus L plus 1, parenthesis. Now, n plus L plus 2, plus, now I will just take the 2 and multiply with that, plus 2n minus 2L minus 2, plus this thing is the common factor, n minus L minus 1, n minus L minus 2, plus 2 of these, plus 2n plus 2L plus 2. So I'm just looking at this. This parenthesis is equal to n plus L plus 1, 3n, 2's cancelled, minus L, plus n minus L minus 1 times 3n, 2's cancelled, minus L plus 2L plus L. Now this has this form: A plus B, C minus D, plus A minus B, C plus D, where A is n, B is L plus 1, C is 3n, and D is L. So I have an AC here, another AC there, 2AC, minus BD, so minus 2BD, but AD will cancel, minus AD, plus AD, and plus BC, minus BC. So we have 2AC minus BD here, which is equal to 2 AC, 3n square, minus BD, LL plus 1, minus LL plus 1. All right. So we obtained, I can erase the right-hand side now. So JNN plus 1 is equal to first term n plus L factorial, n plus L factorial over n minus L minus 1 factorial, that's the front term, times 2 times 3n square minus l plus 1. All right, we will stick that into here. So I will erase this part. Equals. Now we insert the value of normalization coefficient, n over 2, 12 plus 3 times 2n times n plus l factorial over n minus 1 factorial times n over 2, 12 plus 4 times that n plus l factorial divided by minus 1 factorial 2, 3n square minus l plus 1. So n plus l factorial goes, n minus l minus 1 factorial goes, 12 plus 3, 12 plus 4, so this goes away, and that power goes away. And n cancels this n, and 2 cancels this 2. So the result is R and L is equal to 1 over 2 3n square minus l plus 1. Or, if you want R physical, this is dimensionless. R physical and L is 1 over 2 3n square minus L plus 1 A0. All right, let me erase this one and write our results. So, 1 average is 1, from which we obtained n and l, to the normalization constant, which was the same as we obtained using the recursion relation. Then we obtained 1 over r, which is 1 over n square. And then we obtained 1 over r square, which is 1 over n cubed l plus a half. And then we obtained r is 1 half 3n square minus l plus 1. Now, these are the examples I chose in the computation of r to the s. Of course, you can go to higher powers, and in the literature you can find with more sophisticated methods, let's say, for other powers. But at least this was a good exercise. I think we used the generating function, and at least the computation is not too hard, and one does not find it in books so much. At least we can do the few powers, low powers, inverse or direct powers, using this generating function method. Thank you.